Okay. Oops. So let's resume our discussion about compactness. So limit point compactness. So if you remember, I told you this was kind of like the historic definition of compactness from kind of like the end of the 19th century. It's actually slightly weaker in general than compactness. And we say that a space is limit point compact if every infinite subset of X has a limit point. So if you think of that, again, you should always kind of think of the unit interval as kind of like your prototypical compact space. So if you just have an infinite number of points in a unit interval, there is going to be some limit point. So kind of around the same time, there was this idea of sequentially compact. And so that's the idea. This is kind of like the Bolzano-Weierstrass kind of idea that you have some sequence of points in a space. Then if you can have a subsequence, which is just like you just take some increasing sequence of positive integers. Then a space is called sequentially compact if every sequence of points of X has a convergent subsequence. And this is actually, it looks very similar to limit point compactness, but actually it's a little bit stronger. And it's actually a little bit different from compactness. Sequentially compact spaces started looking pretty good, right? Because it satisfies the uniform continuity theorem. So, i.e., if you've got a continuous function on a sequentially compact space, then it's uniformly continuous. And it satisfies the extreme value theorem, right? So, a continuous function on a sequentially compact space attains its extrema. It satisfies the Lebesgue number lemma. We'll actually prove that later. I.e., if you've got a cover, there exists this Lebesgue number, such any set. Of course, and the image of a sequentially compact space is sequentially compact. But it is a little bit different from compact. So there are spaces which are compact, but not sequentially compact. And there are spaces which are sequentially compact, which are not compact. And later on, we'll look at an example of a space which is compact, but not sequentially compact, to kind of see why our definition of compact is the correct one. Basically, when that school of Soviet mathematicians started looking at compactness in the early 20th century, the thing that they found most useful was applying things to function spaces. So that's like an important area where this kind of topology is looked upon. And it turns out that when you do that, our definition of compactness for about every cover, every open cover having a finite subcover, that turns out to be the most useful. Okay. And so just to remind you again what these things mean, a limit point of a set A is a point X such that every neighborhood of X meets A in some point other than itself. And what we mean for convergence, so we say a sequence converges to X if every neighborhood of X contains the tail of X of that sequence Xn, i.e. there exists a capital N such for all little n bigger than big N, those Xn's lie in that neighborhood. And so the general way to think about it is So limit point compactness is weaker than both of those. So we'll see that sequentially compact and compact imply limit point compactness. It's not true the converse, and these kind of things, as I said, there are spaces which are one but not the other. But a very important result says that in a metric space, these three concepts are all the same. And so that's actually useful because it gives you a useful way to prove that some space can't be a metric space. So if you've got a space which is compact but not sequentially compact, then you know that you cannot put a metric on it, which is useful. So before we actually prove things, let's have a look at a few interesting examples. So here, the first one is a kind of trivial thing where we've got a space which is limit point compact, but not compact or sequentially compact. So let's just look at the positive integers, the product space of that with the 2-point set. And on the 2-point set, we'll put the indiscrete topology. So its only open sets are the empty set and the whole set itself. And this is limit point compact trivially, right? Because every subset has a limit point, right? Because we put the indiscrete topology on 0, 1. So if you look at the point, for example, n cross 0, if you just look at n cross 0, that's going to be in the same neighborhood. That's going to have n cross 1 as a limit point, just because we've got the indiscrete topology. So any neighborhood containing the 0 is also going to contain its kind of twin there. So that's going to be trivially limit point compact, but it's not compact, right? Because what do we have to show that it's non-compact? We just have to come up with an open cover. So if we just look at n cross 0, 1, that's an open set in this topology. And so if we let our collection A be that all collection, that's an open cover of a thing, but of course there can be no finite subcover. Okay. Another example of something which is limit point compact but not sequentially compact this time is, let's have a look on the topology of R generated by this set here. We give that a name. I think it was in an example in a problem way earlier when we first looked at things. That is limit point compact, right? So in fact, if you have any subset of R, then if you've got any element, let me write this down. So that's our subset of R. We want to have a limit point of that. So if any x which is greater than any element of A is the limit point. Or is it less than? Yes, right. Because let's say that's an element of our big A, and here's our X here. Any neighborhood then containing X is going to contain A, and so it's a limit point. And of course, this is sequentially compact, because if we just look at the sequence N, and 1, 2, 3, 4, 5, 6, 7, etc., that has no convergent subsequence. So those examples, well, they're okay. A little bit boring, but not anything too deep. Let's have a look at a few examples which are a little bit more deeper. So remember this minimal uncounted well-ordered set S omega. That's an example of a set which is sequentially compact but not compact. Okay. Now, it's kind of obviously that it's not compact because it doesn't have a largest element. So that if you just have an increasing, if you just look at a collection of sections of that set, where alpha is increased, because it doesn't have a maximal element, you can come up with an open cover then of that set. And since there's no maximal element, you can't get a finite subcover. So it's obvious that this set is not compact. What's harder to see is that it's sequentially compact. Well, let's say we have some sequence in S omega. And so we look at this. We look at the set of the points of the elements of this sequence. It's a countable subset. And so by the definition of S omega, it has a upper bound. Let's call that alpha. This, remember, has so if you let A0 be the minimal element of S omega, then just consider the closed interval A0 to alpha. This is a order topology, so it's Hausdorff. This is a closed interval, so therefore it's compact. So this whole space is not compact, but this subspace of it is compact. And then so since it's compact, we'll see in a little bit that it's limit point compact, but also it's sequentially compact because it turns out that this is a metric space. It's metrizable. But we won't be able to prove that until later in the course when we get to Euroson's lemma. We'll be able to show that this is metrizable. But since it's metrizable, it's both compact, limit point compact, and sequentially compact. But because they're sequentially compact, this sequence that we have here of S omega is actually a sequence in this compact space here. So therefore and since it's a metrizable, it's sequentially compact. Therefore, it has a convergent subsequence. So pursuant to theorems that we're going to prove later, this is an example of a space which is sequentially compact, but not compact. another interesting example, and this is really an example which shows that our definition of compactness is the correct correct definition of compactness. So this space here, so this is a function space, right? This is a space of functions from the unit interval to the unit interval. Okay, and we'll consider it in the product topology. Now, that's going to be compact by Tikhonov's theorem, right? Which says that in the product topology, products of compact sets are compact. But I'm going to show you now that it's not actually sequentially compact. And so Tikhonov's theorem, the fact that that is true, this shows you then that in the product topology, the product topology, the product of sequentially compact spaces are not sequentially compact. And so that's really, I think, the main reason why this is then taken as the definition of compactness. So because of that Tikhonov theorem. So in topology, really, the two most important theorems that we'll have in this class is the Tikhonov theorem and Urysohn's lemma, which shows you when things can be metrizable. Okay, so why is this not sequentially compact? Okay, so let's define some functions then from 0, 1 to 0, 1. Okay, so Fn is going to be an element of that product space. We're going to define it by Fn of x equals 0 or 1. It's equal to 0 if nth digit of binary expansion is 0, and 1 if nth digit of binary expansion is 1. Okay, so for this to be well defined, when we talk about binary expansion, so to get unique binary expansions, we're going to ignore expansions with infinite ones at n. Right, because you know, with whenever you talk about the expansion of a number, right, if you've got 0.11111 repeating, that's actually the same thing as 1.0. Okay, so there is non-uniqueness in binary expansion, so we just ignore that. And we just call that, do that. Okay, so to get uniqueness, you either have to ignore infinite ones at the end or infinite zeros at the end. Let's just ignore infinite ones. So what does Fn of x look like? All right, so F1 looks like 0 to a half, and then from a half to 1, it looks like that. So it looks like kind of like that step function there. F2 looks like we have 0, we have a quarter, a half, 3/4, 1. Looks like this. Oops, then it's So it's like piecewise continuous function alternating between 0 and 1. Okay, so let's consider the sequence Fn. So it's a perfectly good sequence of functions. And so as it goes, you know, it starts breaking up more and more and more, and like F infinity is kind of like 0 and 1, basically. It's the same place. That doesn't really exist, but that's what it's going towards. Okay, so I want to show that this does not have a convergent subsequence. Notice, though, since it's compact and it's an infinite set, it does have a limit point. And I think the limit point is the 0 function, but it gets kind of hard to I got a headache trying to think about it, but I think it's a 0 function. But I didn't find it hard to prove. But anyway, let's prove that it doesn't have a convergent subsequence. So the first thing we've got to think about it, what does it mean to converge in the product topology? So in the product topology, this was I think a question in the third homework, and basically convergence in the product topology is pointwise convergence. So Fn converges to F if Fn of x converges to F of x for x in 0, 1. That's not the case in the box topology. In the box topology, it's hard to get anything to converge. In fact, I think Fn converges to F only if Fn differs from F at a finite number of places. So Fn's got to equal F at all but a finite number of places for something to converge in the box topology. So that's another reason why the box topology is kind of useless. Things don't converge in there. But you get, so it's just pointwise convergence. So that's nice and straightforward. So what we've got to do is we've got to find a point in 0, 1 where the subsequence does not converge to anything. And that's actually not that hard. Let's say we're given any subsequence F in K. So what we're going to show is that for any subsequence, we can construct a point where that subsequence cannot converge. Okay. So what do we got? So let's have a look at the indices. So we've got N1 versus N2 versus N3. So we've got a whole bunch of these points. So let's Z be the point 2 to the minus N 2 J minus 1. So what we're doing is so Z equals 0, a bunch of zeros and then 1, a bunch of zeros, then 1. Right, and so this is at the N first index point, this is at N third, this is the N fifth. So it's equal to 0 everywhere except at the odd index points in this subsequence. Okay, now let's have a look what Fn of Z does. Okay, so F1 of Z is 1, F2 of Z is 0, F3 of Z is 1, F4 is 0, F5 is 1, N6 is 0. In particular, F odd at Z is always going to be 1, and F even at Z is always going to be 0. So kind of like by construction, this always alternates between 0 and 1, so this never converges. It's NK. That subsequence there never converges. So it's actually quite pretty. And so if it doesn't converge at this point, then the whole subsequence can't converge. So it is not sequentially compact. Great. Okay, let's do a few results. Sequential compactness implies limit point compactness. That's actually not so hard. So let's say we have a sequentially compact space, a sequentially compact space, and let's say we have an infinite subset V, and we want to show that V has a limit point. Okay? So let's just take a sequence of points in V, any sequence of points in V. Since it's sequentially compact, this X is a limit of a convergent subsequence of that sequence. And X is then a limit point of V, right? Because any open neighborhood of X intersects with infinitely many of the Xn, i.e. all the points that are in the tail of that subsequence. So that's good. So that's straightforward. Compactness implies limit point compactness. Okay, so the same thing. So actually, we're going to prove it differently. So let's say we have a compact set. We're going to prove the converse. Let's say we have a subset A having no limit point. So let's prove that A has to be a finite set there. Okay. Well, if A has no limit point, then A is closed because it contains all its limit points, i.e. right? Then for each A in our closed set, we can choose a neighborhood of A which intersects that space only at A. That's the whole point of not having a limit point. We can find a neighborhood where it doesn't intersect with another point. That gives us an open cover of X, right? By X minus A, because A is closed, X minus A is open, and all these little open neighborhoods. Therefore, we can have a finite subcover. X minus A doesn't include anything in A. So we've got a finite cover then of A, and each of our finite cover only includes one element of A, so therefore A has to be finite. That's quite nice. Okay. So we can see straight away why limit point compactness is kind of weaker than the other two. Okay, so in order to be able to prove that in a metric space sequentially compact is the same as compact, we need to prove the Lebesgue number lemma. and i.e. that the Lebesgue number lemma holds for sequentially compact spaces, i.e. if we have any open covering of a metric space, if X is sequentially compact, then there is a Lebesgue number, i.e. each subset having diameter less than the Lebesgue number is in an element, is wholly contained in an element of A. And it's a proof by contradiction. Okay, so let's assume that there's no such delta. So that means for each n, we can choose a set with diameter less than 1 on n that is not contained in any element of, entirely contained in an element of A. Okay. So let's call that set Cn. And we're just going to choose a point xn in Cn. Right, because it's sequentially compact, we've got to come up with a sequence if we've got to prove it. Okay, so we've got a sequence of elements. So we have a subsequence which converges to some point. Okay, so it converges to some point A. So A has to be an element of some element of our cover. Of our open cover. Okay, but A is an open set, so that means we can put a little epsilon ball around A and still remain within A. Now we get into trouble, right? Because remember the way we set up C of n is that we've got this diameter less than 1 on n. So if I is large enough, then 1 on ni is going to be less than epsilon on 2, right? Because these diameters are getting smaller and smaller and smaller, so that at some particular point we can get less than epsilon 2, right? So that means this set CNI lies entirely within that neighborhood of that point in the subsequence. But again, if I is large enough such that the distance from xni to A is less than epsilon on 2, right? And that can happen because the subsequence is converging to A. That means that xni's are getting closer and closer to I. Then that set CNI lies within the epsilon on 2 neighborhood of A. That tells us that this set here is wholly contained within A, contradicting our definition of what Cn was. So again, we see that just because there's a metric space, you can do a lot with the metric space. Okay, and so here's our big theorem for this section. So if you've got a metric space, i.e. you've got a space that you're able to put a metric on it that will give you the topology of that space, then all these three things are equivalent. Okay, so we've already proved, so for any space, 1 implies 2 and 3 implies 2. So what we've got to prove is that 2 implies 3 and 3 implies 1. We've just got to do those two things and we're done. So we've got to show that a limit point compact is sequentially compact and sequentially compact is compact. Okay, limit point compact is sequentially compact. Okay, so we've got our limit point compact space X, because we're assuming 2, and so we have some sequence of points in there. So we've got to show that there is a convergent subsequence. Okay, so now let A just be the set of elements of our sequence. If A is a finite set, that means there must be some xn which is repeated infinitely number of times. So we have a constant subsequence. That's a good enough to be a convergent subsequence. So we can assume that A is infinite. But if A is infinite, then since it's a limit point compact space, we have a limit point X. And so now we can do the thing that we like to do with metric spaces. We just take balls of diminishing radius. Okay, so we choose an n1 such that xn1 is within 1 of x. And then we just get smaller and smaller. Then we choose our next one such that the next element is within 1/2 of x, and then 1/3, 1/4, and now we've got a subsequence which is convergent to x. So the fact that x is a limit point and that we have a metric space, we can now use that to find a convergent subsequence. So that's not hard at all. So the trickiest one actually is to show that 3 implies 1. That sequentially compact implies compactness. Okay. So another thing that's nice about sequentially compact spaces is that if you've got any cover of a sequentially compact space by epsilon balls, there is a finite subcover. And that's not so hard to do because if there wasn't a finite covering of, so remember it's the same epsilon. So it's so otherwise, let's say that fails. So that there exists an epsilon greater than 0 such that there's no finite covering of x by those epsilon balls. We then just construct a sequence, right? It's sequentially compact, so that's how we prove the completion. Do a sequence. So we let x1 be any point. We let x2 to be any point not in the ball around x1 of radius epsilon. And then we just proceed by induction. Right? Given n points in our sequence, we choose our nth by 1 to be any point not in the union of the previous epsilon balls. Since there's no finite subcover, we can go on for infinity, and so that gives us a sequence. Right? But this sequence has no convergent subsequence, right? Because all the points are more than epsilon away from each other. So that's how we get our contradiction. Okay, and so now we can, with that lemma, we can now prove that sequentially compact implies compactness for metric spaces. So so to prove compactness, we're going to show that every open cover has a finite subcover. So let's say we have our open covering. We know from the previous lemma, since it's a sequentially compact space, that that open cover has a Lebesgue number delta. So we let epsilon equal delta divided by 3. And then we have a finite covering of X by open epsilon balls. But each of these balls, right, lies in an element of A. The elements of A are actually bigger than the epsilon balls. So if the epsilon ball, if the finite cover of epsilon balls covers X, then their finite partners also cover X. And so this gives us a finite subcollection. So we just choose one element for each of the epsilon balls, and that gives us our finite subcollection. Yep, that's pretty good. So the cool thing about that is we get a corollary. So if we have a space that has one of the compactness properties, but not all three, then it is not metrizable. So for example, all the examples that we looked at before cannot be put, cannot have a metric put on them. Including this one, which is, so the interesting one is kind of, is this one. So remember, we use the fact that the closed interval in it is metrizable to show that it was sequentially compact. But since the whole thing is not compact, the whole space is not metrizable. And very interestingly, this function space here can't have a metric put on it. Okay, so that'll do us for today.